Now we're going to do some optimization problems. What optimization problems are problems where I have given constraints that limit what I can do, but an objective function which I'm trying to either maximize or minimize. Optimization problems answer the question, what is the maximum or minimum value of an objective function subject to the given constraint or constraints? Here's an example. What pair of non-negative numbers maximize the value of them multiplied together if they must add to 20? So I'm going to first come up with my objective. My objective is the number equals x times y, where x and y are my two different numbers. My constraint, that's simply 20 equals x plus y. So what do I do with this? Well, I've got two different variables, and I've got two different equations. So let me first take my constraint and solve it for x. X is equal to 20 minus y. I'm now going to take that and plug it into my objective function. This works out to be 20 minus y times y, or 20y minus y squared. I know that my values for x and y, well, actually I only care about y in this case because I'm down to a single variable. I know y has to go between 0 and 20 because it's non-negative, and the two numbers must add to 20. So I have my interval. I can also find the maximum value of this function by taking the first derivative. N prime is equal to 20 minus 2y. So, to find my critical points, in this case there would just be one of them, I set my first derivative equal to 0. Solving for y, I get that y is equal to 10. If y is equal to 10, since x plus y must equal 20, that means x is also equal to 10. So how do I find the maximum value? If I have a closed interval like I do, I need to check what happens when y equals 0, when y equals 10, and y equals 20. Let's come up with the corresponding x values. And now I'm going to plug them into my objective function. And I find that my maximum value is when x is equal to 10 and y is equal to 10. And that number, when I multiply them together, is equal to 100. So this maximized my objective of two numbers multiplied together, given a constraint of x plus y having to equal 20. Let's do another example. Let's say a farmer wants to build 3 rectangular pens for his pig. One side of the pen will be the side of his barn. The other 3 sides and the 2 interior walls will be made with the 400 meters of fencing material that the farmer has available. What should the dimensions of the pen be in order to maximize its area? Before we do anything, let's draw a sketch. I've got the barn and the 3 sides of the fence. I know I want to break this into 3 pens, so I'm going to also have 2 interior walls. I'm going to label each of the short walls y and the length of the horizontal piece x. I need to figure out my objective function as well as my constraint function. I'm going to start with the constraint. I know I have only 400 meters of fencing material available to me, and what that fencing will be is my length x plus 4 pieces of the y components. My objective is to maximize the area. The area is simply equal to x times y. Now that I have my objective and my constraint functions, I can go ahead and solve this. What I'm going to do is take the constraint function, I'm going to solve it for x, and I'm going to plug that into my objective function. Once I do that, I get that the area is equal to 400y minus 4y squared. I need to take the first derivative of that area in order to maximize it. I'm going to find my critical points. To find my critical points, I'm going to take that first derivative and set it equal to 0 and solve for y. When I do that, I find that y is equal to 50, and in order to find x, I plug that back into our constraint function, substituting y is equal to 50, and I find that x is equal to 200. If I want to graph this, I'm going to have to think about what the domain of this function is. That is, what are my values of y that are allowed? I know that y can go from 0 to 100. I get the 100 from setting x equal to 0 in the constraint and solving for y. At my maximum point, 50, 200. At my maximum point, 50, 200, the area is 10,000, so that gives me my window in which to graph. And if I look at my graph, I do in fact find that my maximum value is there. So in order to maximize my area, I'll set each of those sides to 50 meters and the long piece at 200. Let's do another example. An airline allows boxes that can only have a maximum sum of length, width, and height not to exceed 64 inches. What dimensions should the box be to maximize volume? The way the problem is set up, I would have an objective function of the volume being the length times width times the height, and the constraint being that 64 equals L plus W plus H. The trouble is, I'm not going to be able to solve a problem like this, because I can't take one variable and solve it in terms of another. So I'm going to be a little more specific with this. That is, I'm going to say that the bottom of the box must be a square. So that means the length and the width will be the exact same value. Now that I have it in this form, I'll do the exact same thing that I did for the previous problem. I'm going to take the constraint. I'm going to solve the constraint for h and plug it into my objective function. And this is what I get for my volume. Now I'm going to go ahead and find the first derivative and set it equal to 0 to find the critical points. In this case, I'm going to have to factor first. I can even pull out another 2, and I get two separate values. One w being 0, and the other w being 64 divided by 3. With w being 0, h has to be 64, and when w is 64 over 3, I find that h is also 64 over 3. If I plug those into my volume, I find that the volume is equal to 0 when w is 0, and the volume is equal to 64 over 3 to the third power, or approximately equal to 9,709 inches cubed. If I graph this, I find that 64 over 3 is in fact a local maximum. That point of 0 is a critical point, but that's the local minimum. Let's do another example. Let's say I have a house and a 8-foot fence that's 3 foot away from the base of the house. I need to get a ladder to reach the side of the house. I'm trying to minimize, in this case, the length of the ladder. What I'm going to do in this case is use similar triangles. Let's say I've got two triangles here. I have that triangle, and then I have this triangle. What I'm going to let equal x is the distance of the foot of the ladder from the fence. So this side of the triangle is given by x plus 3. The length of the ladder I'm going to call L, and the height along the house I'm going to call B. That's not part of my requirement. What I'm trying to find is the shortest ladder that will still touch the house anywhere along that side of the house. Using the Pythagorean theorem on my larger triangle, I see that L squared is equal to B squared plus x plus 3 all squared. Using similar triangles, I see that the side B is to the side of 8 foot, as x plus 3 is to x. Again, the b and the x plus 3 are from my larger green triangle, and my 8 and my x are from the smaller red triangle. So what I can do with this is solve for b. Once I know b, I can take this and plug it into my Pythagorean theorem. I say I can factor out an x plus 3, specifically an x plus 3 squared, and what's left behind is 8 over x all squared plus 1. Now I should be taking the first derivative of my L, not my L squared, but because this has to stay a positive function, I can't have negative length for a ladder, I can actually just maximize the L squared and get the same value, and that's going to be a lot easier than taking a square root. So the derivative of L squared, I'm going to set that equal to 0, and that's equal to the derivative with respect to x of everything that I have in parentheses. I've rewritten 1 over x squared as x to the negative 2 power to make it easier to take the derivatives. I'm going to have to use the product rule in this case, followed by the chain rule, so let's go ahead and do that. If I factor out an x plus 3 and simplify what's left in the parentheses, I get the derivative down to this. Again, I'm going to set this equal to 0. The x plus 3, setting that equal to 0 would give me a negative 3. We can't have that. So that means my answer is the cubed root of 192, or approximately 5.77. I could use the first derivative test to show that this is in fact a local maximum. When I plug 5.77 into my equation for L squared and take the square root, I find that the length of the ladder will be about 15 feet.